A thermonuclear supernova is supposed to leave no body behind. A white dwarf reaches a critical limit, its carbon ignites, and within seconds the whole star is meant to tear itself apart so completely that nothing remains. No core, no ember, nothing at all. That is the rule, and yet drifting through our galaxy right now, there are stars that seem to have broken it. Battered, chemically scrambled, and hurled outward at hundreds of kilometers per second. They look exactly like objects that should have been vaporized, except they are still here, still glowing, still held together by their own gravity. Something detonated them, and somehow they refused to finish dying. So what exactly are these survivors? And how does a star walk away from the blast that was supposed to destroy it? If stories like this one, the strange, barely believable corners of the cosmos, are the kind of thing you enjoy, a quick like or subscribe genuinely helps this channel keep going. No pressure at all, but it makes more of a difference than you'd think. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. There is a kind of death in the universe so violent, so total, and so reliable that astronomers have turned it into a ruler. When a particular kind of dead star explodes, it does so with almost the same brightness every single time, anywhere in the cosmos, which means that if you measure how bright it looks from Earth, you can work out exactly how far away it is. These explosions have been used to map the shape of the universe itself, to measure how fast space is stretching, to weigh the darkness pulling galaxies apart, and the entire method rests on one quiet assumption that nobody really questioned for decades. The assumption is that the star is gone, not damaged, not wounded, gone, converted in a few seconds into an expanding cloud of glowing debris and scattered to the void, with nothing left at the center. No ember, no core, no survivor. That is the rule, and it is a good rule, because most of the time it is exactly what happens. But the universe, as it turns out, keeps a few stars that did not read the rulebook. Scattered through our galaxy, moving far too fast, carrying a chemistry that no ordinary star should ever have on its surface. There are objects that look for all the world like the leftovers of an explosion that was supposed to leave nothing behind. They are battered. They are deformed. Some of them are being thrown clean out of the Milky Way at hundreds of kilometers per second. And yet they are still there, still glowing faintly, still holding themselves together under their own gravity. Something tried to annihilate them. Something lit them on fire from the inside and detonated them. And somehow, they refused to finish dying. People sometimes call these objects zombie stars, and the name has been used loosely enough that it can mean almost anything. So let's be precise from the very start about what we mean here, because precision is the whole point of the story. When we talk about a zombie star, we are not talking about a neutron star, the city-sized ball of crushed matter left behind when a giant star's core collapses. We are not talking about a star that quietly fizzles and fails to explode at all. We are not talking about an ordinary nova, a small surface flash that leaves the star underneath untouched. And we are absolutely not talking about anything biologically alive, restored, or healed. What we mean is something far stranger and far more specific. We mean a dead star that was set off as a thermonuclear bomb, that burned only part of itself, that blew a chunk of its own body into space, and that nonetheless held onto a surviving, gravitationally bound core. A remnant of an explosion that was supposed to be complete, but wasn't. To understand how that is even possible, we first have to understand the kind of star this happens to, and why it is one of the most dangerous and delicately balanced objects in all of nature. The star at the center of this story is a white dwarf. To picture one, you have to start with an ordinary star like our own sun. For most of its life, a star like the sun is a careful balancing act. Deep in its core, hydrogen is fusing into helium, and that fusion releases an outward push of heat and radiation. At the same time, the star's own enormous weight is constantly trying to crush it inward. These two forces, the outward push of fusion and the inward pull of gravity, hold each other in a near-perfect standoff for billions of years. But fuel does not last forever. Eventually the core runs low, the fusion in the center sputters, and the balance breaks. A star like the sun will swell into a red giant, shrug off its bloated outer layers into space, and leave behind only its naked, exhausted core. That exposed core is the white dwarf. Now here is where the numbers stop making intuitive sense. A white dwarf packs something close to the entire mass of the sun into a ball roughly the size of the Earth. Think about that for a moment. The sun is so large that more than 1 million Earths could fit inside it. Take most of that mass, all of it, and crush it down until it is no bigger than our small rocky planet. The result is a density so extreme that a single sugar cube-sized piece of white dwarf material would weigh about as much as a car, perhaps more. A teaspoon of it would weigh tons. It is matter compressed to a degree that simply does not exist anywhere on Earth. Not in the heart of any laboratory, not at the bottom of any ocean. And it raises an obvious question. If gravity is strong enough to crush an entire sun down to the size of a planet, what stops it from crushing it further? What holds a white dwarf up, now that its fusion fire has gone out and there is no more outward push from burning fuel? The answer is one of the most beautiful and counterintuitive ideas in physics. And it is the key that unlocks this entire story. A white dwarf is not held up by heat. It is held up by a rule about how the smallest pieces of matter are allowed to behave. Inside that crushed core, the atoms have been squeezed so hard that their electrons have been stripped loose and packed together into a dense sea. And electrons, it turns out, are profoundly antisocial particles. There is a fundamental law of nature which says that two electrons cannot be forced into exactly the same state, in the same place at the same time. They refuse. You can push them closer and closer, but at a certain point they push back with a ferocity that has nothing to do with temperature and everything to do with this stubborn refusal to overlap. This resistance is called electron degeneracy pressure, and it is what holds the white dwarf rigid against the relentless inward crush of its own gravity. The star is not burning. It is not generating heat to support itself. It is being propped up purely by the unwillingness of its electrons to be squeezed together any tighter. That sounds like a stable, peaceful arrangement, and in many ways it is. A white dwarf left to itself will simply sit there, slowly radiating away its leftover heat over billions upon billions of years, cooling and fading like an ember, pulled from a fire and set on a shelf. But this strange pressure that holds the star up comes with a hidden flaw, a property so dangerous that it turns the white dwarf into a loaded weapon, waiting for a trigger. And to see why, we need to understand what makes a normal star safe, so that we can appreciate exactly how a white dwarf is not. In an ordinary living star, there is a built-in safety mechanism, a kind of natural thermostat. Imagine the core of the sun suddenly fusing fuel a little faster than usual. That extra fusion dumps in extra heat. The extra heat raises the pressure. The higher pressure pushes outward, so the core expands slightly. And here is the crucial part. When a normal gas expands, it cools down. As the core cools, the fusion rate drops back toward normal, the pressure eases, and everything settles. The reverse works too. If the core cools and contracts, it heats up and fusion speeds back up. Heat causes expansion, expansion causes cooling, and the whole system gently corrects itself, over and over, for billions of years. This is why stars are so stable. A small disturbance gets damped out automatically. The thermostat keeps the fire under control. A white dwarf has no such thermostat. This is the single most important fact in the entire story, so it is worth sitting with. Because the white dwarf is held up by degeneracy pressure rather than by heat, its pressure barely responds to temperature at all. You can pour heat into degenerate matter and it will not expand the way a normal gas would. The pressure is set by how tightly the electrons are packed, not by how hot they are. So picture what happens if you somehow manage to light a nuclear fire inside this material. The fire dumps in heat, the heat raises the temperature, but the star does not expand to relieve the pressure and cool itself off, the way a normal star would. It just gets hotter while staying the same size, and hotter material fuses even faster. Faster fusion makes even more heat. More heat makes it hotter still. There is no expansion, no cooling, no correction. The safety valve is simply gone. The fire feeds on itself, accelerating wildly, the temperature climbing toward billions of degrees in a runaway cascade that nothing inside the star can stop. This is what physicists mean by a thermonuclear runaway, and it is the difference between a controlled burn and a bomb. So a white dwarf is a ball of nuclear fuel, carbon and oxygen, packed to unimaginable density, with the one safety feature that keeps every other star stable deliberately switched off by the laws of quantum physics. All it needs to become a catastrophe is a push. It needs to be lit. And on its own, a typical white dwarf will never light, because it is not quite massive enough or hot enough at its center to start fusing its carbon. It will just cool quietly forever. But white dwarfs are not always left alone. Many of them live in pairs, locked in orbit with a companion star, and that is where the trigger comes from. There are a few different ways nature can pull the trigger, and the details will matter enormously later. But the basic idea is simple. If a white dwarf can gain mass, things change. Perhaps it has a close companion star, a living, bloated neighbor, and the white dwarf's intense gravity slowly siphons gas off the surface of that companion, pulling it down onto itself like a thief, skimming fuel. Or perhaps two white dwarfs orbit each other, spiraling closer and closer over millions of years until they collide or one tears the other apart. Either way, the white dwarf's mass creeps upward, and as it gains mass, its own gravity squeezes its core harder and harder, driving the central temperature and density up. There is a famous limit to how much mass a white dwarf can carry before this crushing becomes unbearable. A critical mass of roughly 1 4/10 times the mass of the Sun, known as the Chandrasekhar limit. But why should there be a limit at all? If the stubbornness of those packed electrons is what holds the star up, why can't it simply hold up more and more mass forever, growing ever more crushed, but never giving way? The answer is one of the most elegant and unsettling results in all of physics. And it comes down to a hidden cost buried in how that electron pressure actually works. The electrons resist being squeezed together by moving, by darting about at tremendous speeds, and the harder you compress them, the faster they are forced to move in order to keep pushing back, pile on more mass, and gravity squeezes harder. The electrons answer by racing faster still. For a while, this works beautifully. The electrons always managing to move quickly enough to resist. But there is a ceiling on speed in the universe, a speed that nothing can exceed. The speed of light. And as more and more mass is heaped onto the white dwarf, its electrons are driven faster and faster until they begin to approach that ultimate limit. Here is the trap. Once the electrons are moving at nearly the speed of light, they can no longer respond to extra crushing the way they used to, because they have almost nowhere left to go. No more speed left to gain. Their pressure stops climbing fast enough to keep pace with the relentlessly growing weight pressing down on them. Gravity, which has no such ceiling, keeps getting stronger as the mass rises. And at a certain point, gravity wins. There is a maximum amount of mass that electron pressure can ever support, a hard, fixed ceiling set by the speed of light itself, and that ceiling is the Chandrasekhar limit. It is not a gentle threshold, but a true point of no return. A white dwarf that creeps up to it is a structure whose support is about to fail. An object holding itself together by a pressure that is running out of room to grow. This is why approaching the limit is so catastrophic rather than gradual, and why it is precisely there, at the brink of collapse, with the core squeezed to unbearable density and temperature, that the carbon finally lights. As a white dwarf is pushed toward that limit, the pressure and heat at its center climb, until finally, deep in the core, the carbon ignites. And because there is no thermostat, that is the end. The instant fusion takes hold in that degenerate core. The runaway begins. Within seconds, a wave of nuclear burning sweeps through the star, fusing carbon and oxygen into heavier elements and releasing a torrent of energy. The temperature does not gently rise, it explodes upward to billions of degrees. In the span of a heartbeat or two, the star fuses a substantial fraction of its entire body, and the energy released is staggering, almost beyond comprehension. It is enough energy to outshine an entire galaxy of hundreds of billions of stars. It is enough to be seen across the observable universe. And crucially, it is enough to do something to the star that nothing else in its existence ever could. It is enough to tear the white dwarf completely apart. This is the standard outcome, the textbook explosion, the death we began with. In the classic version of this event, called a Type Ia supernova, the energy unleashed by the runaway fusion is far more than enough to overcome the gravity binding the star together. Every particle in the white dwarf gains so much speed that it can escape from every other particle. The star does not merely crack or shatter, it is unbound. The matter is flung outward in all directions at tremendous speeds, typically somewhere between 5,000 and 20,000 kilometers per second. That is fast enough to cross the distance from the Earth to the Moon in a matter of seconds. It is a meaningful fraction of the speed of light itself, around 6%. The debris races away, glowing fiercely as freshly forged radioactive elements decay and pour out light, and over weeks and months it fades into a slowly expanding remnant. But at the center, where the star used to be, there is nothing. No core, no surviving ember. The white dwarf has been entirely consumed and dispersed. It is, in the most literal sense, gone. This is why these explosions make such good cosmic rulers. Because the trigger involves a white dwarf reaching that same critical mass limit, and because the explosion consumes the whole star so thoroughly, the events tend to release almost the same amount of energy and shine with almost the same peak brightness every time. They are nature's standard candles, beacons of nearly identical wattage scattered across cosmic history. Measure how bright one appears, compare it to how bright you know it truly is, and the difference tells you the distance with remarkable precision. It was by measuring these very explosions in distant galaxies that astronomers discovered, to their astonishment, that the expansion of the universe is speeding up. A discovery that reshaped all of cosmology. And every bit of that depends on the explosions being complete. It depends on the star being fully destroyed, leaving no awkward survivor behind to muddy the brightness, no leftover core to complicate the accounting. Total annihilation isn't just the expectation, it is the assumption baked into one of the most important measurements humanity has ever made. So now you can feel the full weight of the contradiction. Here's an object engineered by physics to be perfectly destructible. A ball of nuclear fuel with its safety valve removed, primed to undergo a runaway fusion fire the moment it is pushed past a limit, releasing enough energy to scatter itself to the winds. The whole logic of the explosion says complete. The whole point of these stars as cosmic rulers says complete. And for the brightest, most famous versions of these events, complete is exactly what we see. By every reasonable expectation, when a white dwarf detonates as a thermonuclear supernova, there should be no survivors, ever. The body should always be gone, and yet the survivors exist. We have found them. Not as a theoretical curiosity, not as a maybe, but as actual objects in our sky that you can point a telescope at right now. There are stars drifting through the galaxy whose chemistry is a fingerprint of nuclear burning. Stars dusted in the ashes of fusion that should only ever be created in the heart of a thermonuclear explosion. There are stars that are unbound from the Milky Way, hurtling outward fast enough to escape the gravity of 300 billion stars, with no good explanation for their speed, except that something violent flung them. There are stars that are bloated and overheated and chemically scrambled in precisely the way you might expect if they had been caught in a blast and survived it. The universe, it seems, does not always finish what it starts. Sometimes the bomb goes off and something walks out of the fire. How can that be? How can an explosion powerful enough to unbind an entire star, an explosion whose defining feature is its completeness, leave a core behind? The white dwarf has no thermostat to throttle the burning back. The runaway should consume everything. So either our picture of the explosion is missing something, or there is more than one way for a white dwarf to die. And some of those ways are messier, weaker, and stranger than the clean total annihilation that makes such a perfect cosmic ruler. The answer, as you might already suspect, is the second one. Not every thermonuclear supernova is the same. Some of them are fainter, some of them are slower. Some of them, it appears, burn only a part of the star before something goes wrong, before the fire stumbles and stalls and fails to do the one thing it is supposed to do, which is to take the whole star with it. To understand the survivor, then, we have to understand the failure. We have to look at a quieter, dimmer, less famous kind of stellar explosion. One that for a long time was lumped in with its brilliant cousins, until astronomers slowly realized it was playing by different rules. It is a kind of explosion where the runaway fire does not sweep cleanly through the entire star, where the geometry of the burning is lopsided and incomplete, and where the energy released, though immense, is somehow not enough or not arranged in the right way to unbind everything. It is a class of event that hints at a flame that can be lit, can do tremendous damage, and can still leave the core of the star standing in the ruins. That weaker, stranger explosion, this fainter cousin, sometimes called a Type Iax supernova, is where our survivors are born. And the secret to how a star can endure its own destruction lies in the precise, almost delicate way that this lesser fire moves through degenerate matter, burning and stalling, consuming and sparing, in the handful of seconds that decide whether a white dwarf becomes a scattered cloud of dust or a battered, glowing fugitive fleeing the scene of its own death. That is the secret we're going to unravel. We've established the rule, and we've established that the rule is broken. We know what a white dwarf is: an Earth-sized ember holding the mass of a sun, propped up by the stubbornness of its own electrons, with no safety valve to stop a fire once it starts. We know why. When such a star is pushed past its limit and its carbon ignites, the burning runs away into a blast bright enough to be seen across the cosmos. And we know that the expected result, the textbook result, the result our cosmic rulers depend on, is a star erased so completely that nothing remains at the center. The only thing left to explain is the impossible part. How a star can be lit, can detonate, can throw off its outer layers into space, and can still survive as a bound, wounded, chemically transformed remnant. To do that, we have to follow the flame itself, second by second, as it begins to burn through the doomed star, and then, against everything we would expect, begins to fail. To understand how a star survives its own explosion, you have to stop thinking about the explosion as a single event, and start thinking about it as a process. A bomb does not detonate everywhere at once. A fire does not consume a forest in a single instant. There is always a front, an edge, a moving boundary where the unburned fuel meets the fire. And that boundary travels. How fast it travels, how it moves, whether it speeds up or stalls, whether it sweeps cleanly through everything or sputters out partway, these are the details that decide everything. And in the heart of a dying white dwarf, those details are the difference between a star that is erased and a star that endures. For a long time, astronomers did not think these details mattered very much, because the explosions they were watching all looked reassuringly similar. A white dwarf was pushed past its limit, the runaway fire ignited, and the result was a brilliant, predictable flash that faded in a characteristic way, bright, fast, and consistent. The same energy, the same speeds, the same fading curve, again and again. That consistency was the whole reason these explosions made such reliable cosmic rulers. So when a fainter, stranger explosion turned up, the first instinct was to treat it as a slightly defective version of the usual thing. A normal explosion that had simply underperformed. That changed in the year 2002, with a supernova that refused to behave. It appeared in a distant galaxy, and when astronomers studied its light, almost everything about it was wrong. It was far too faint, glowing at only a fraction of the brightness a normal thermonuclear supernova should reach. Its debris was moving too slowly, expanding outward at speeds well below what the textbook explosion demanded. And the fingerprints in its light, the signatures of which elements were present and how they were moving, did not match the familiar pattern. This object, catalogued as SN2002CX, was so peculiar that it eventually became the prototype, the founding member of an entirely new category of stellar explosion. Astronomers came to call this class Type Iax, supernovae. They were clearly cousins of the bright, standard Type Ia explosions, born from the same kind of doomed white dwarf, lit by the same kind of runaway nuclear fire. But they were the dimmer, quieter, slower members of the family, weaker explosions. And over the years that followed, more of them were found, dozens of them, enough to make clear that this was not a fluke or a handful of oddities, but a genuine and recurring way for a white dwarf to die. The faintness was the first clue, and it pointed straight at the mechanism. A supernova's brightness comes from how much of the star actually burns, because the light is powered by the radioactive decay of freshly forged elements created in the fusion. A bright explosion means a lot of the star was converted into those glowing radioactive ashes. A faint explosion means only a little of it was. So the dimness of these strange supernovae was telling astronomers something remarkable and specific. It was saying that in these events the fire was not consuming the whole star. It was burning only part of it. The runaway, which is supposed to be unstoppable, which is supposed to take everything, was somehow stopping short. And if the fire stopped short, if it burned only a fraction of the star and then quit, then there was a tantalizing possibility lurking in that unburned remainder. There might be something left. To see how a fire can stop short inside a star that has no safety valve, we need to understand the two fundamentally different ways that burning can travel through fuel. They are called deflagration and detonation, and the distinction between them is the single most important idea in this entire story. They sound like technical jargon, but the difference between them is something you can picture with things from everyday life, and once you see it, the whole mystery starts to come apart. Imagine a long trail of gunpowder laid out on the ground, and you touch a flame to one end. The fire catches and begins to race along the trail, igniting the powder grain by grain as it goes. The burning travels as a front, a moving edge of flame that eats its way forward, heating the next bit of fuel until it too catches, and so on down the line. This is a deflagration. It is, in essence, an ordinary flame, a burning front that propagates by heating the fuel just ahead of it until that fuel ignites in turn. The crucial feature of a deflagration is that it is subsonic. The burning front travels slower than the speed of sound in the material. That might sound like a dry technical point, but it has an enormous consequence, and here it is. Because the front is moving slower than sound, the fuel ahead of it gets advance warning. Sound waves, which are really just pressure signals, race out ahead of the slow-moving flame and ripple through the unburned fuel before the fire arrives. The fuel feels the pressure building. It has time to respond. It can move, it can shift, it can expand and get out of the way before the flame ever reaches it. Now imagine something very different. Instead of a trail of gunpowder, imagine a stick of dynamite, and instead of lighting it gently, you set off a violent shock. The burning does not travel as a gentle flame creeping forward. It travels as a shock wave, a wall of crushing pressure that slams through the material faster than sound can carry any warning. This is a detonation. The defining feature of a detonation is that it is supersonic. The shock front outruns its own warning signals. The fuel ahead of it has no idea what is coming, no time to respond, no chance to move or expand or get out of the way, because the pressure signals that would carry that warning cannot travel faster than the shock that is generating them. The shock arrives first, slamming into fuel that is still sitting at full density, crushing and igniting it instantly. A detonation does not give the material a chance. It catches everything flat-footed, at full strength, all at once. That difference, whether the burning front moves slower or faster than sound, whether the fuel gets a warning or gets caught off guard, turns out to decide the fate of an exploding white dwarf. And to see why, you have to remember what we already know about these stars. That their pressure is set by how tightly their matter is packed, and that the energy released by burning depends critically on how dense the fuel is when the fire reaches it. Dense fuel burns more completely and releases more energy. Thin, spread out fuel burns poorly and releases less. So the question of whether the fuel has time to expand and thin out before the fire arrives is not a minor detail. It is the whole game. In the bright, standard explosion, the one that erases the star completely, the burning manages to reach the fuel while it is still dense. The lean picture for how that happens is that the fire starts as a deflagration, a subsonic flame, but at some point it makes a violent transition. It speeds up, crosses the sound barrier, and becomes a detonation. Once that detonation forms, it is unstoppable. The supersonic shock races through the rest of the star, slamming into the still dense interior before that material has any chance to expand and escape, igniting it at full density and extracting the maximum possible energy from it. The detonation burns the star to completion, releases the full torrent of energy, and unbinds every last particle. That is the clean, total annihilation. That is the perfect cosmic ruler. The detonation is the executioner that leaves no survivors. But here is the part that has unsettled physicists for the better part of a century. Nobody is entirely certain how that violent transition happens, or why, in some stars, it never does. Turning a slow, subsonic flame into a supersonic detonation is not a small adjustment. A gentle flame and a crushing shockwave are profoundly different things, and coaxing one to spontaneously become the other, buried deep inside a star, in the span of a single second demands very particular conditions. The flame has to whip itself into such a frenzy of turbulence that a pocket of unburned fuel gets heated and squeezed in exactly the right way, at exactly the right density, in exactly the right geometry, to suddenly run away as a shock rather than a flame. Physicists call this the deflagration to detonation transition, and despite enormous effort poured into some of the most demanding computer simulations ever attempted, the precise recipe for it remains genuinely uncertain. It is one of the real open frontiers of the whole field. We can see that it must happen in the bright, complete explosions, because those stars are fully consumed. But we cannot yet say with confidence exactly what conditions tip a churning flame over that edge, and what conditions leave it stranded on the wrong side. And that uncertainty is not a weakness in the story. It is the story. Because if the conditions are not quite right, if the density is too low, if the turbulence does not organize itself in just the necessary way, then the leap may simply never come. The flame stays a flame. The shock never forms. And the star is left to face a fire that can burn, but cannot finish. But what if the fire never makes that jump? What if the flame starts as a subsonic deflagration, as it always does, and then simply stays a deflagration? What if it never crosses the sound barrier, never becomes a detonation, never gains the speed to catch the dense interior off guard? This is the leading idea for what happens in these fainer explosions, and it is where the story turns. A pure deflagration, A flame that burns and burns but never transitions into the supersonic killer that would finish the job. And a pure deflagration, it turns out, is a profoundly inefficient way to destroy a star. Because it is subsonic, because it is slow, because it gives the fuel ahead of it all the warning in the world, it sets in motion a chain of events that can cause the fire to defeat itself. Here is how. When the deflagration ignites, it does so not as a neat spherical shell expanding smoothly outward, but, in the most favoured models, as a small off-centre bubble of fire lit somewhere away from the dead centre of the star. This burning bubble is intensely hot, and hot material is buoyant, just as a hot air balloon rises through cooler air, or a blob of heated wax rises through a lava lamp. This bubble of nuclear flame is lighter than the dense, cold, unburned matter around it, and so it rises. It floats upward toward the surface of the star, churning and billowing as it goes. As it rises, it breaks apart into plumes and fingers and swirls, a process driven by what is called the Rayleigh-Taylor instability. The same kind of instability that makes a dense fluid sitting on top of a lighter one break into descending fingers and rising bubbles. The flame becomes a wild, turbulent, billowing mess of rising fire, wrinkled and stretched and folded over on itself, racing toward the surface rather than burning steadily down into the dense heart of the star. And all the while, the star is responding. Remember, this is a subsonic flame, which means the pressure waves it generates are racing out ahead of it, warning the rest of the star that energy is being dumped in. The unburned matter feels this and does exactly what the warning allows it to do. It expands. The whole star begins to swell, to puff outward, lifting and thinning under the pressure of the energy being released by the rising flame. This is the fatal flaw in the deflagration, the self-defeating move. As the star expands, its density drops everywhere, and a nuclear flame, like any fire, needs fuel at sufficient density to keep itself going. As the expanding star thins out, the density ahead of the flame falls, and at a certain point, it falls below the threshold the fire needs to sustain itself. The flame can no longer ignite the fuel in front of it, because that fuel is now too spread out, too thin, too rarefied. And so the fire goes out. The deflagration quenches itself. The runaway, which had no thermostat to stop it, found another way to stop. It expanded the star until it strangled its own flame. Think about what just happened, because it is genuinely strange and genuinely beautiful. The white dwarf had no safety valve. We established that. Heat could not make it expand and cool the way a normal star does, which is exactly why the fire could run away in the first place. But once enough of the star has actually burned, once the deflagration has dumped in enough energy, the star does finally expand. Not because of a gentle thermostat correcting a small imbalance, but because a violent fire has poured so much energy into it that the whole structure heaves outward. And that late violent expansion is what finally chokes the flame. The fire burns long enough and hard enough to inflate the star, and the inflated star puts out the fire. The bomb partially detonates, and then, in the act of partially detonating, blows out its own fuse. The result is a star that has been only partially burned. The off-center bubble rose, churned, and consumed a chunk of the star on its way up and out, but it never burned down through the dense central regions, and it quenched before it could finish. So you are left with a star that has a burned, processed portion full of the heavy ashes of nuclear fusion, and an unburned or partially burned portion that the fire never fully reached before it died. This is why these explosions are so faint. Only part of the star was converted into the glowing radioactive ash that powers the light, so there is less light to give. And this is why their debris moves so slowly. The energy released was a fraction of what a full detonation would unleash, so the material is not flung out nearly as fast, expanding at speeds of perhaps a few thousand kilometers per second, rather than the much higher velocities of a complete explosion. Everything about these supernovae that looked wrong, the faintness, the slowness, the strange chemistry, traces back to this one fact: the fire did not finish. There is a wrinkle in the fuel itself worth pausing on, because it quietly shapes everything that comes after. We've been speaking of the white dwarf as a ball of carbon and oxygen, and for the most common white dwarfs, that is right. But white dwarfs come from stars across a range of masses, and the ones born from the heavier end of that range can end up with a different recipe inside them. As the star that made them lived out its final stages, it managed to fuse its carbon a little further, leaving behind a core enriched not just in oxygen, but in neon and magnesium as well. These are sometimes called hybrid cores, and they matter here for two reasons. The first is that neon-rich, oxygen-rich material burns under somewhat different conditions than pure carbon and oxygen, which can influence how willing the flame is to keep going, and how readily it might or might not make that fatal leap to a detonation. The second reason is subtler, and will echo through the rest of this story. If a fire sweeps only partway through a star whose interior was already rich in oxygen and neon, and then quenches, the survivor it leaves behind will carry that signature on its body. An outer chemistry dominated not by the hydrogen and helium of an ordinary star, but by oxygen and neon, the very stuff of its unburned and partially burned guts. We are, in other words, already glimpsing why the survivors look the way they look, before we have even met one. The strange chemistry that will let us recognize these objects in the sky is being written in this moment, in the composition of the fuel that the fire failed to finish. But the most important consequence is the one we have been building toward this whole time. When you tally up the energy, two things have gone wrong from the explosion's point of view. Two things that together open the door for a survivor. First, less of the star burned, so less energy was released overall. And second, a great deal of the energy that was released did not go into flinging matter apart at all. It went into lifting and expanding the star, into the work of puffing the whole structure outward. Energy spent on inflation is energy not spent on annihilation. So when you add it all up, the explosion may simply not have enough left over to do the one thing it is supposed to do, which is to unbind the entire star, to give every particle enough speed to escape the gravitational grip of every other particle. The outer regions, the parts caught up in the rising, churning flame and the expanding debris, do get enough of a kick to be thrown off into space. That material escapes. That becomes the faint, slow-moving cloud of ejecta we see glowing as the supernova. But the central regions, the deep core that the fire never properly reached, may never gain enough speed to break free. And so it stays. It remains gravitationally bound. The explosion threw away a part of the star and kept the rest. This is the heart of the entire phenomenon, the mechanism that makes a zombie star possible. It is not that the explosion was secretly gentle, or that the white dwarf was somehow protected. The explosion was real and violent, and threw a portion of the star into the cosmos at thousands of kilometers per second. It is that the explosion was incomplete, the fire, by remaining a slow subsonic deflagration rather than transitioning into a supersonic detonation, defeated itself before it could finish, expanding the star until it choked off its own burning. It released enough energy to wreck the star, to scramble its chemistry, to blow off its outer layers and light up a galaxy for a while. But not enough, and not in the right configuration to unbind the whole thing. And what survives, held together by gravity in the wreckage at the center, is the bound remnant, a core that was lit on fire, partially consumed, and left behind. It is worth pausing here to be careful, because precision matters and the universe is rarely as tidy as a single clean story. This picture, the off-center pure deflagration that fails to detonate, expands the star, quenches itself, and leaves a bound remnant, is the leading model for how these fainter Type Iax explosions work. And it is supported by detailed computer simulations that reproduce many of the strange features astronomers observe. But it is a model, an interpretation of what the physics and the simulations and the light curves are telling us. Not something anyone has watched happen up close in slow motion. There are open questions and competing ideas about the exact details, about precisely how the flame ignites and where, about how much burns and how much survives, about whether every one of these explosions works the same way, and critically the connection between this kind of incomplete explosion and an actual surviving star is something we will have to weigh carefully against real observations rather than simply assume. For now, the key idea is the mechanism itself, the logic of incomplete thermonuclear destruction, and that logic is sound. A subsonic flame that strangles itself by inflating the star it is trying to destroy can, in principle, leave a bound core behind. The question of whether the survivors we actually see in the sky truly are such cores is one we will come to. Notice too, what this story is not, because the differences matter and it is easy to blur them. This is not a star whose core collapsed. There is no implosion here, no crushing of matter inward into something denser, no neutron star or black hole forming at the center. That is a completely different kind of stellar death. The death of a massive star whose core gives way under its own weight, and it has nothing to do with what we are describing. What we are describing is the opposite in spirit. An outward explosion, a thermonuclear fire that simply failed to carry through to completion. The energy went outward, blowing material off into space. It just did not go far enough to take the whole star. The survivor is not something crushed into existence by collapse. It is something spared by an explosion that ran out of steam. Keeping that distinction clear is essential, because the words supernova and remnant get used for both stories, and they could not be more different in what actually happens. And there is one more feature of this incomplete explosion that we have only touched on, but that turns out to be enormously important. A feature that will give the survivor its most dramatic and detectable signature. Remember that the flame in the favored picture ignites off-center as a single bubble lit somewhere away from the heart of the star and rises and burns its way out toward one side. That means the explosion is not symmetric. It is lopsided. The matter is not blown off evenly in all directions like a balloon popping uniformly. It is blown off preferentially toward one side, like a rocket venting its exhaust in a single direction. And just as a rocket is pushed forward by throwing its exhaust backward, a star that throws off a chunk of itself in one direction can be shoved hard in the opposite direction. The asymmetry of the explosion does not just shape the debris, it can give the surviving core an almighty kick, a recoil powerful enough to fling the battered remnant away from the site of its own near-death at tremendous speed, sending it tumbling out across the galaxy as a runaway. So we now have the full shape of the mechanism. A white dwarf is pushed to ignition. The fire begins as an off-center, subsonic deflagration. Buoyant and turbulent, it billows upward and outward, burning part of the star while pouring energy into the structure. That energy inflates the star, the density drops, and the flame strangles itself before it can transition into the detonation that would finish the job. A portion of the star, burned and processed and full of nuclear ash, is flung off into space as a faint, slow, lopsided cloud of debris. But the deep core, never fully reached by the dying flame, never given enough of a kick to escape, remains gravitationally bound. And the very lopsidedness of the blast may hurl that bound survivor away at high speed. The bomb went off. It just did not go off the way it was supposed to. It burned part of the star, kept the rest, and threw the leftovers across the galaxy. That leftover is our zombie star. But to call it a survivor is not to call it whole. It did not walk away from this clean. It was lit on fire from within. It was partially consumed by nuclear burning. It was inflated and shaken and contaminated by the ashes of fusion, and then flung into the void carrying the chemical scars of an event that should have ended it. Whatever emerges from the wreckage of an incomplete thermonuclear explosion is not the white dwarf that went in. It is something altered, something wounded, something that bears in its size, its temperature, its motion, and above all its chemistry, the unmistakable marks of having been through a catastrophe and lived. And it is precisely those marks, those scars written into the body of the survivor, that allow us to find these objects, to recognize them for what they are, and to read in them the story of the explosion they endured. What that wounded survivor actually looks like, how the fire reshapes it, how the nuclear ashes settle into its outer skin, why it glows hotter and larger than it has any right to, and how a star that was nearly destroyed ends up racing through the galaxy faster than the galaxy can hold onto it, is where the trail leads next. The word survivor is a generous one. It conjures something that walked away from danger, dusted itself off, and carried on more or less intact. But that is not what comes out of an incomplete thermonuclear explosion. What comes out is closer to a wreck. To picture it properly, you have to hold two ideas in your mind at the same time, and they sit uneasily together. The star was not destroyed, and the star was nearly destroyed. Both are true. It endured, and it was ruined in the enduring. Everything that makes a zombie star recognizable, everything that lets us pick one out of a sky full of ordinary stars, is a scar left behind by the catastrophe it lived through. So let us take the wreck apart piece by piece and read its injuries, because each one tells part of the story of the fire that almost finished it. Begin with the most intimate wound, the one written into the very substance of the star, its chemistry. Remember what a white dwarf was before any of this happened. It was a cold, dense ember made mostly of carbon and oxygen, the leftover core of an ordinary star, with perhaps a thin outer skin of lighter elements, clean, simple, unremarkable in composition. Now consider what the deflagration did to it. The fire swept through part of the star, and where it burned, it did what nuclear fusion always does. It forged the light elements into heavier ones. Carbon and oxygen were cooked into a whole spectrum of new material, into neon and magnesium, into silicon and sulfur and calcium, and in the hottest, deepest reaches of the burning, into the iron group elements, iron and nickel and their radioactive cousins. These heavier elements are the ash of nuclear fire, the residue left behind when fusion runs its course. And in a complete explosion, all of that ash would have been blown clean off into space, dispersed into the expanding cloud of debris, scattered to seed future stars and planets. But this explosion was not complete. The fire stopped short, and so a great deal of that ash had nowhere to go. It settled, it fell back, it coated and infiltrated the surviving core. This is why the survivors look so profoundly wrong when we examine the light they give off. Every element imprints its own unique fingerprint on starlight, a pattern of dark and bright lines that reveals which atoms are present in a star's outer layers. When astronomers read the fingerprint of an ordinary star, they see hydrogen and helium, the common stuff of the cosmos, the raw material that stars are built from. When they read the fingerprint of these survivors, they see almost none of that. Instead, they see an atmosphere dominated by oxygen and neon, with no detectable hydrogen and no detectable helium at all, and sprinkled through it, the unmistakable signatures of the heavier ashes of incomplete burning, the silicon and the iron group metals that should only ever be created in the heart of a thermonuclear explosion. These are some of the most chemically peculiar stars known anywhere, so saturated with the byproducts of nuclear fire that they rank among the most metal-rich objects astronomers have ever catalogued. Their surfaces are not the surfaces of stars. They are the surfaces of explosions. There is a particular detail in this chemical wreckage that turns out to be a kind of signature, almost a confession, and it is worth dwelling on because it shows how much a single element can reveal. Among the ashes detected in these survivors is manganese, present in quantities far above what you would find in the sun or in any normal star. Manganese is not a casual ingredient. It is forged in specific conditions, in burning that happens at the very high densities found near the crushing center of a white dwarf that has been pushed close to its critical Chandrasekhar mass before igniting. The presence of so much manganese is therefore a clue about the explosion's origin, pointing toward a white dwarf that was near that maximum mass when it lit. And it lines up with what theoretical calculations predict such an explosion should produce. The chemistry is not just strange, it is strange in exactly the way the incomplete explosion story requires. The wound matches the weapon. But contamination is not the only thing the fire did to the body of the star. It also changed its shape, and this is the second great wound. The survivor is swollen. A normal white dwarf, as we have said, is a tightly packed ember about the size of the Earth, perhaps 100th the radius of the Sun, crushed down and held rigid by the stubborn pressure of its degenerate electrons. It is one of the most compact forms of ordinary matter in existence. The survivors of these explosions are nothing like that. They are bloated, puffed up, inflated to many times the size of an ordinary white dwarf. In the best studied cases, the surviving star has a radius perhaps 15 times larger than a typical white dwarf, which means it is no longer a planet-sized ember at all, but something far larger and far more distended. A swollen ghost of the compact core it once was. And the reason for this inflation goes straight back to the physics that made the whole disaster possible in the first place. Recall the strange secret of degenerate matter. That its support comes not from heat, but from the packing of its electrons, which is precisely why a white dwarf can sit cold and rigid for ages, and why it has no thermostat to stop a runaway fire. That rigidity holds as long as the matter stays degenerate. But the explosion poured an immense amount of energy into the surviving core, and there are several ways that energy lingers in the wreckage. The blast itself shocked and heated the star. Radioactive material created in the burning, and some of the debris that fell back onto the survivor continues to decay, pumping out heat from within like a buried coal. And all of that heat does something important. It partially lifts the degeneracy. When you heat degenerate matter strongly enough, it begins to behave a little more like an ordinary gas again. A gas that responds to temperature, a gas that wants to expand, and so the survivor swells. The energy of the explosion, deposited into a core that could not simply shrug it off, has inflated the star far beyond the compact dimensions it held before. It is, in a real sense, still reeling from the blow, still puffed up by the violence done to it, a star caught in the act of recovering from being lit on fire. That inflation connects directly to the third wound, which is that the survivor is too bright and too hot for what it is. By rights, the leftover core of a partially burned, low-mass white dwarf should be a dim and modest thing. Instead, these objects glow more fiercely than a quiet white dwarf of similar mass has any business doing, and they run hot. Part of that is the swelling itself. A larger, more distended star presents more surface area to radiate from. Part of it is the heat still trapped inside, the lingering warmth of the explosion, and the slow burn of radioactive decay continuing to leak energy outward. The survivor is luminous not because it has rekindled any kind of sustained nuclear furnace in its core, but because it is a body that absorbed a tremendous shock of energy and is now slowly bleeding that energy back out into space, glowing as it cools, like a forged piece of iron pulled from the fire and left to radiate in the dark. It is a star powered, for the moment, by its own near death. So already we have a portrait of something deeply altered. A core stripped of the normal hydrogen and helium that ought to cloak a star. Its surface instead caked in the heavy ashes of nuclear burning, bloated to many times its former size, overheated, overbright, and chemically unlike anything that forms by ordinary stellar processes. If a survivor like this simply sat still in space, it would already be a striking oddity. But the survivors do not sit still. They move. And the way they move is perhaps the most dramatic scar of all. Because it turns a chemically strange object into something openly violent in its behavior. A fugitive tearing across the galaxy at a speed that betrays exactly what happened to it. To understand the motion, we have to return to the shape of the explosion, because the asymmetry that we touched on earlier is what launches the survivor. Picture again how the fire is thought to begin. Not as a symmetric shell expanding evenly in all directions, but as a single bubble of flame ignited off to one side of the star's center, which then rises and burns its way out toward that side. The burning is lopsided. The material that gets blown off is blown off preferentially in one direction, vented out across one face of the star, while the opposite side is comparatively spared. And here is where a simple and powerful piece of physics takes over. The same physics that flies a rocket. When you throw mass forcefully in one direction, you're pushed in the other. A rocket rises by hurling exhaust downward. The downward exhaust is matched by an upward shove on the rocket. The exploding star, venting a great gout of burned material out across one side, experiences the same kind of recoil. The ejection of matter in one direction kicks the surviving core in the opposite direction. The lopsided blast does not just shape the debris cloud, it shoves the survivor hard, like a cannon firing and rolling backward on its carriage. That recoil is one source of the survivor's speed, but it is not the only one. And the second source is just as important to understand because it shapes how we interpret what we find. These exploding white dwarfs are very often not solitary. The whole reason a white dwarf gets pushed to ignition in the first place, as we saw, is usually that it has a companion, a binary partner from which it has been stealing mass, locked with it in a tight gravitational orbit. And in many of these systems, that orbit is extraordinarily tight, the two stars whirling around each other in a matter of hours, sometimes circling their common center in not much more than a single hour. To stay in such a close, fast orbit, an object has to be moving at a tremendous orbital speed, hundreds of kilometers per second, simply to keep from falling into its partner. Now imagine the explosion goes off and disrupts that delicate arrangement. Whatever survives is suddenly released from the orbital dance, flung free of the binary like a stone whirled on a string when the string is cut. Whatever speed it had as it swung around its partner, it keeps, carrying that orbital velocity with it as it flies off into space. Between the rocket-like recoil of the asymmetric blast and the orbital fling of being released from a tight binary, the survivor can be set loose at truly enormous speed. How enormous? Enough for it to outrun the galaxy. Our Milky Way holds its stars with gravity, and to break free of that grip from where the sun sits, a star would need to be moving at something like 500 to 600 kilometers per second, depending on exactly where it is. That is a colossal speed, far beyond the gentle orbital drift of ordinary stars, which circle the galactic center in stately fashion at a couple of 100 kilometers per second relative to their neighbors. Yet some of these survivors have been clocked moving faster still, fast enough that the galaxy cannot hold them at all. They are unbound, on a one-way trip outward, destined to leave the Milky Way entirely and wander into the dark between galaxies, never to return. A star that has been lit on fire, partially consumed, chemically rewritten, inflated, and overheated, and then flung out of its own galaxy by the force of the blast that nearly ended it. The wreck is not only a wreck, it is a wreck in headlong flight. There is a subtle but crucial point hidden in that flight, and it is the kind of detail that separates careful astronomy from a good guess. The galaxy is already known to harbour a small population of extremely fast-moving stars, and for those, there is a well-understood culprit. At the very centre of the Milky Way sits a supermassive black hole, and a star that strays too close to it can be slingshotted outward at ferocious speed by a gravitational encounter, flung away from the galactic centre like a rock from a sling. So whenever astronomers find a star racing through the galaxy, an obvious first question arises. Did this thing get its speed from a close call with the central black hole? For the survivors we are discussing, the answer turns out to be no, and the reason is geometric. If you trace the path of one of these fast survivors backward through space, rewinding its motion to see where it came from, the trajectory does not point back to the galactic center. It comes from somewhere else, somewhere out in the disk of the galaxy where the black hole could not have flung it. That single fact, that the motion does not trace back to the center, is a powerful piece of evidence. It rules out the easy explanation and points instead toward exactly the kind of event we have been describing. A violent ejection from a binary system out in the body of the galaxy. An explosion that kicked the star loose right where it lived. The survivor's path through space is, in effect, a return address, and the address is not the black hole. It is the scene of an explosion. Even the way the survivor spins carries information, and this is where the anatomy becomes almost forensic. When two stars orbit each other extremely closely, their rotation tends to become locked to their orbit. So that the surviving star, at the moment it is set free, ought to be spinning rapidly, inheriting a fast twirl from the frantic orbital motion it was just released from. Astronomers can measure how fast a distant star rotates, and so the spin of a survivor becomes another clue to be weighed against the story. In at least one well-studied case, the survivor is found to be turning relatively slowly, completing a rotation over a period of hours rather than whirling at breakneck speed. And that measured spin has been used to argue about which object in the original binary the survivor really is, and what kind of explosion set it loose. The point is not the specific number, it is that every property of these objects, the chemistry, the size, the temperature, the speed, the direction of travel, and even the rate of spin, is a piece of evidence, a thread that ties the surviving star back to the catastrophe that made it. The survivor is not just an oddity, it is a record. Hear carefully, its body is a transcript of its own near destruction. Now, having assembled this portrait, we have to be honest about the boundary between what we observe and what we infer, because that boundary is where good science lives and where it is easiest to overreach. What we observe, directly and undeniably, are the properties of certain peculiar stars. Their strange chemistry dominated by oxygen and neon and dusted with nuclear ash, their bloated radii, their elevated temperatures and luminosities, their extreme velocities, the directions they are traveling, their rates of spin. Those measurements are real. They are not in serious doubt. What is an interpretation, a model, a proposed history, is the claim that these stars are the bound remnants of incomplete thermonuclear explosions. That story explains the observations beautifully, perhaps better than any alternative, but it is a reconstruction of a past event from present clues, the way a detective reconstructs a crime from the evidence at the scene. The chemistry is consistent with partial nuclear burning. The inflation is consistent with energy deposited by an explosion. The velocity is consistent with a kick from an asymmetric blast and ejection from a tight binary. The trajectory is consistent with an origin out in the galactic disk rather than a slingshot from the center. Each piece fits. But fitting a story is not the same as having watched the story unfold, and the careful astronomer holds that distinction firmly in mind. These are leading candidates, compellingly explained, not closed cases. That caution matters all the more because there is a genuine ambiguity hiding inside the survivor story, one that even the experts wrestle with. And it concerns which star we are actually looking at. In these violent binary explosions, there can be more than one survivor in principle, and they are very different objects with very different histories. There is the surviving core of the white dwarf that exploded, the partially burned remnant we have been describing, the thing that was lit on fire and not fully consumed. But there can also be a surviving companion, the partner star that was sitting nearby and got blasted by the explosion but was not itself the bomb. And in certain configurations involving two white dwarfs, The surviving partner can be flung away at even more staggering speeds, well over 1,000 kilometers per second, not because it burned, but simply because it was orbiting so fast and so close when its companion detonated that the disruption hurled it outward like a slung stone. These extreme runaways are surviving donors, not surviving bombs. They are leftovers of the explosion, but they are not the partially burned core. They are the bystander that was flung clear. Telling these two kinds of survivor apart, the burned remnant versus the flung companion, is one of the real challenges in the field, and it is exactly where clues like the chemistry, the rotation, and the precise velocity earn their keep. A star coated in the ashes of nuclear burning is hard to explain as an innocent bystander. That chemistry points to a body that was itself burned. The slowness or speed of the spin, the exact velocity, the detailed composition, all of these are weighed to decide whether a given runaway is the wounded core of the exploded star or the kicked out partner that merely stood too close. Hold on to that distinction, because it is one of the easiest things to blur, and one of the most important to keep straight. Not every fast, strange star fleeing the galaxy is a zombie star, in the sense we have carefully defined. Some are surviving donors, partners flung free without ever having been lit. The true zombie star, the object at the center of this whole story, is the one whose body bears the chemistry of fire, the partially burned core that was supposed to be annihilated and was not. That is the survivor whose anatomy we have just dissected. The contaminated chemistry, the swollen and overheated body, the runaway flight kicked off by an asymmetric blast, and an unraveled binary. The trajectory that points back not to the galactic center, but to the scene of an explosion in the disk. Every one of those features is a wound, and every wound is consistent with the same cause, a thermonuclear fire that did tremendous damage, and then failed to finish. And there is one more thing to say about this anatomy, because it changes how we should think about the object's future, and guards against a misunderstanding the very word zombie invites. This is not a star brought back to life. Nothing has been restored, nothing healed, nothing rekindled into a new and lasting existence. The survivor is not glowing because it has reignited a sustained nuclear furnace and begun a fresh chapter as a living star. It is glowing because it is hot from being wounded, swollen from being shocked, and slowly leaking away the energy of the disaster that nearly destroyed it. It is, in the truest sense, a corpse that has not yet finished cooling, a body lit by the residual heat of its own catastrophe. The word zombie is a vivid metaphor, and a useful one for catching the imagination, but it should not be taken to mean that the star is alive in any meaningful way, or that it has been resurrected. It died in the explosion. It simply did not disintegrate. What persists is the wreckage, glowing for now, carrying its scars across the sky. So that is the wounded survivor, laid bare. A core that should not exist, betraying its history in every measurable property. In a chemistry saturated with the ash of fusion, in a body bloated and overheated by absorbed violence, in a headlong flight out of the galaxy launched by a lopsided blast and a shattered binary, in a trajectory that confesses where it came from, even in the rate at which it turns. We have built the picture from physics and from the leading models, and we have been careful to mark where observation ends and interpretation begins. But a picture built from reasoning is one thing. A real object you can point a telescope at is another. The natural question, The one that decides whether any of this is more than an elegant theory is whether such survivors truly exist out there. Whether astronomers have found stars whose strange properties match this anatomy so closely that the incomplete explosion story becomes hard to deny. The answer is that they have. There are specific objects in our sky, with names and measured properties and contested histories, that wear these wounds. And it is to those real survivors, to what we have genuinely seen and what we are still arguing about, that the trail now leads. Everything we have built so far is a chain of reasoning. A white dwarf with no thermostat, a fire that begins as a slow flame and chokes itself before it can finish. A wounded core flung across the galaxy wearing the chemistry of its own near destruction. It is an elegant story, and the physics behind it holds together. But elegance is not evidence. A story that explains everything and predicts nothing you can actually find is just a fable with equations attached. So the real question, the one that decides whether any of this is true, is brutally simple. Can we point a telescope at the sky and find one? Is there an object out there, a real star with a real name and real measured properties, that wears the wounds we have described so faithfully that the story stops being a story and becomes a fact? There is. And the first and most important of them carries the unglamorous catalogue name LP4365. It does not look like much in any image, a faint point of light among countless others, easy to overlook for decades, which is exactly what happened. But when astronomers finally turned a careful eye on it and read the fingerprint in its light, they found something that should not exist. The star had almost no hydrogen and no helium, the common building blocks that cloak nearly every ordinary star. Instead, its atmosphere was dominated by oxygen and neon, and laced through that strange chemistry were the heavier ashes of incomplete nuclear burning, the products of partial oxygen and silicon fusion. This was not the surface of a normal star. It was the surface of an explosion, the chemistry of a fire frozen onto the body of a survivor. It is, by some measures, one of the most metal-rich stars ever found, so saturated with the byproducts of fusion that it stands apart from essentially every other star in the catalogues. Then they measured how it moves, and the strangeness deepened into something almost shocking. LP4365 is not drifting lazily along with its neighbours in the slow communal orbit that ordinary stars share around the galactic center. It is tearing through space at roughly 850 kilometers per second relative to the galaxy around it. That is not merely fast. It is fast enough to escape the Milky Way entirely, to break free of the gravity of hundreds of billions of stars and fly off into the dark between galaxies, never to return. And when astronomers traced its path backward through space, it passed exactly the test we laid out earlier. Its trajectory does not converge on the galactic center, so the slingshot that launches the galaxy's ordinary hypervelocity stars cannot be responsible. The star came instead from out in the disk, from open territory where the central black hole has no reach, precisely the kind of place a companion detonating beside it would have flung it loose. Its motion, in other words, points not inward toward the center but back toward a blast. And then the measurements that sealed the portrait. Using precise distances from a star mapping space mission, astronomers worked out the physical size of the star, and it was wrong in exactly the way the theory demanded. LP4365 is bloated, swollen to something like 15 times the radius of an ordinary white dwarf, far too large for the compact ember it ought to be, just as you would expect for a core still puffed up by the energy of a blast it had absorbed. Its chemistry says it was burned, its swelling says it was shocked and inflated, its speed says it was kicked hard. Its trajectory says the kick happened out in the galaxy, not at the center. Its slow spin has even been used to argue about which member of the original binary it must have been. Every single property lines up with the same cause, a thermonuclear explosion that did enormous damage and then failed to finish. This one, faint, fast, chemically impossible star, is the leading real-world embodiment of everything we have described. The original discoverers proposed it as exactly that: a partially burned, runaway white dwarf, the surviving remnant of an underluminous thermonuclear supernova. And it is not alone. What began as a single oddity has grown into a small but real class. Astronomers have since found several more stars cut from the same cloth, sharing that same bizarre oxygen and neon chemistry dusted with nuclear ash, the same extreme velocities, at least some of them also unbound from the galaxy and on their way out. A prototype with companions is no longer a fluke, it is a category. These objects, the LP-4365 class, form a distinct family of chemically peculiar runaway remnants, survivors of thermonuclear explosions scattered through our galaxy and, in some cases, already leaving it. The fact that there are several of them, each independently strange in the same specific way, is itself a kind of proof. One impossible star might be a misunderstanding. A growing family of them, all wearing the same wounds, is a phenomenon. And the population is larger than those few runaways might suggest, once you count the explosions, as well as the survivors. The weaker, fainter class of thermonuclear supernova that we have been describing is not some once-in-history rarity. Astronomers have now catalogued more than 30 of these events, flickering in distant galaxies. Enough that they are recognized as a steady, recurring channel of stellar death, rather than a handful of curiosities. And from how often these explosions are seen, you can work backward to an estimate of how often they ought to be minting survivors right here in our own galaxy. The rough figure that emerges is striking. A new one of these objects may be created somewhere in the Milky Way every few centuries to 1,000 years or so. That is frequent enough that the galaxy should be quietly seeded with them. A slow accumulation of battered, fleeing remnants built up over its long history. Most are surely too faint and too far to have been noticed yet. The ones we have found are almost certainly the nearest and the most conspicuous members of a much larger, mostly hidden population drifting through the dark around us. It is worth pausing on how anyone could possibly know all of this about a faint smudge of light, because the answer is a small triumph of patient technique, and it is the kind of detective work that turns a dot in the sky into a life story. The chemistry comes first, and it comes from splitting the star's light apart into its component colors. Spread starlight into a spectrum, and the atoms in the star's outer layers stamp it with a precise barcode of dark lines, each element absorbing its own signature set of colors. Read that barcode, and you can say with confidence which elements are present and roughly how much of each, which is how astronomers can declare of a star many light years away that it has no detectable hydrogen, no helium, and an atmosphere drowning in oxygen, neon, and the ashes of partial burning. The size comes from a different trick entirely. By measuring the tiny shift in a star's apparent position as the Earth swings from one side of its orbit to the other, a precise star mapping mission can triangulate the true distance to the star. And once you know how far away something is and how bright it truly appears, you can work out how large and how hot it must be. That is how a faint point of light is revealed to be bloated to many times the size of an ordinary white dwarf. And the motion, the headlong flight, is reconstructed from two measurements stitched together. How fast the star is drifting sideways across the sky, tracked over years, and how fast it is moving toward us or away from us, read from the subtle stretching or compressing of those same spectral lines. Combine the two and you recover the star's full velocity through space, fast enough, in this cases, to escape the galaxy. Then you run that motion backward, like rewinding a film, to ask where it came from. None of these measurements is dramatic on its own, but laid on top of one another, they convert an anonymous speck into a fugitive with a measured speed, a known chemistry, a calculated size, and a traceable past. But notice what we have and what we do not have. For these runaways, we are hearing the aftermath. We found the survivor long after the explosion, like a detective arriving at a scene years later to study a person who walked away from a catastrophe nobody witnessed. We can read the scars and reconstruct what must have happened, and the reconstruction is compelling, but we never saw the blast. We are inferring the explosion from the survivor. What would be far more convincing, what would close the loop in a way nothing else could, is to find the reverse, to actually watch one of these explosions happen, and then go looking for the survivor in the wreckage. And astronomers have managed, in at least one extraordinary case, to come remarkably close to doing exactly that. The case is a supernova catalogued as SN 2012Z, which detonated in a galaxy about 100 million light-years away. By itself, a faint thermonuclear supernova of this weaker class is interesting, but not unheard of. What made this one historic was a stroke of preparation and luck. The galaxy it appeared in had been photographed years earlier, in fine detail, by a space telescope for entirely unrelated reasons. So when the supernova went off, astronomers had something they almost never have: a clear picture of the exact spot before the explosion. They could go back to the old images, find the precise location where the star had detonated, and see what had been sitting there beforehand. And there, in the archive, at the right place, they found a star system. It was the first time astronomers had ever caught a glimpse of the progenitor of one of these weaker explosions before it blew, a genuine before and after of a thermonuclear supernova. What the old images suggested was a hot blue companion star locked in a tight relationship with a white dwarf, feeding it material, the very kind of arrangement that pushes a white dwarf toward ignition. Then the explosion faded, and the astronomers waited. And here the story turned in precisely the direction the theory predicted. When they returned to look at the site after the supernova's light had died away, they did not find empty space swept clean. The fading of the explosion behaved in a way consistent with a bound, surviving remnant still sitting at the center, an object puffed up and glowing, heated by the lingering energy of the blast and the decay of radioactive material that had fallen back onto it. Rather than vanishing into a uniformly expanding cloud, as a complete annihilation should, the event left signs of something left behind. A battered core that the explosion had failed to disperse. It was, as closely as we have ever come, a direct look at the making of a zombie star, a white dwarf in a tight binary, lit, partially destroyed, and not entirely gone. And yet, even here, honesty demands a caution, because this is exactly the kind of result that is easy to oversell. The behavior of the fading explosion was consistent with the surviving bound remnant, and that is genuinely exciting, but consistent with is not the same as proven beyond doubt. Astronomers found it difficult to build a single complete model that explained every detail of how the light evolved. The survivor interpretation fit the data well, perhaps better than the alternatives, but the picture was not perfectly clean, and the wreckage of a distant explosion is a noisy, complicated thing to read. So even in our best case, where we watched the explosion and went looking for the survivor afterward, the right description is a strong, well-supported case rather than an absolutely closed one. The pattern of the evidence points toward a survivor. It does not hand us one with certainty. This is the texture of real science at its frontier, where the most important results often arrive not as triumphant proofs, but as compelling, carefully hedged likelihoods. That same family of explosions also has a far gentler, far stranger member, one that shows just how wide the range of these events can be. An explosion catalogued as SN2008HA appeared in a distant galaxy and turned out to be one of the faintest and feeblest thermonuclear supernovae ever recorded. So weak and so slow that for a time astronomers were not even sure how to classify it. Its debris crept outward at a fraction of the speed seen in ordinary explosions, and it released so little light that it sat near the very bottom edge of what could still be called a supernova at all. If the brighter, more famous explosions represent a fire that swept through much of the star, an event like this one represents a fire that barely got started, that burned only a small fraction of the star before sputtering toward failure. And that matters for our story because it sketches out a spectrum. At one extreme sits the complete, total annihilation that leaves nothing behind. At the other sits a fire so feeble it scarcely qualifies as an explosion, which ought to leave behind a great deal indeed. The weaker the blast, the less of the star is consumed, and the more substantial the surviving remnant should be. These events are not all the same. They form a graded series from near total destruction to near total survival, and the existence of an explosion as faint as this one is a vivid reminder that the door to leaving a remnant behind can be opened very wide. There is, however, one place where the certainty is far greater, and it sits not in a distant galaxy, but in our own. Centuries ago, in the year 1181, observers in China and Japan recorded the sudden appearance of a new star in the night sky, a temporary guest that flared into view and then slowly faded over months. For a long time, this historical event, catalogued by modern astronomers as SN 1181, was something of a mystery. It remains uncertain. But in recent years, the pieces have come together in a striking way. Astronomers identified a faint, expanding nebula, a delicate cloud of glowing filaments spreading out like the petals of a dandelion, and connected it to that centuries-old guest star. The nebula is catalogued as PA30, and at its very heart, where the explosion must have occurred, there sits a star. That central star is no ordinary object. It is intensely hot, extraordinarily so, and its composition is bizarre, rich in oxygen, a member of a rare and exotic class that astronomers call Wolf-Rayet stars, the kind normally associated with very different and much more massive objects. It shouldn't be there at all if the explosion that created the surrounding nebula had been complete. but it is there, glowing at the center of the wreckage, a survivor of the blast recorded by astronomers nearly 1,000 years ago. The expanding nebula around it, studied in fine detail with modern instruments that can map the motion of its filaments as they stream outward, tells the story of a thermonuclear explosion of the weaker, incomplete kind. And the surviving star at the center is now regarded as a confirmed example of exactly the phenomenon we have been chasing, a remnant left behind by a Type Iax supernova. It is the only such remnant known within our own galaxy, a 1,000-year-old wound with a glowing scar still sitting at its heart. The explosion, documented by human eyes, and the survivor still visible today. But this confirmed case also carries a lesson in humility and in the messiness of nature, because the way this particular survivor came to be appears to differ from the single white dwarf with a feeding companion picture we sketched earlier. The evidence suggests this explosion was born from the collision and merger of two white dwarfs of different compositions, spiraling together and igniting, rather than from a single white dwarf slowly fed by a living partner. And that matters, because it reveals something important about the whole subject. There may be more than one road to a survivor. The incomplete thermonuclear explosion that spares a bound remnant might be reached by a single white dwarf that fails to fully detonate, or by a merger of two that produces a partial blast, or by other channels we are still working out. The destination, a wounded surviving core, can apparently be reached by different paths. This is not a weakness in the story. It is a sign that the phenomenon is real and varied, robust enough to happen in more than one way. But it should keep us from imagining that there is a single, tidy recipe behind every zombie star. The universe, as usual, is more inventive than our cleanest models. We drew this line earlier between the burned core of the exploded dwarf and an innocent bystander flung clear of the blast. But it is worth seeing how those bystanders actually turn up in the real sky, because they form their own remarkable population. The same star mapping mission that pinned down the size of our fugitive remnant has also revealed a separate breed of runaway. Stars hurtling outward even faster, at more than 1,000 kilometers per second, on trajectories that point back not to the galactic center, but to ordinary spots out in the disk. These are widely interpreted as surviving donors, and the leading idea for how they are launched is genuinely different from the failed deflagration we have been tracing. In that scenario, both stars in the binary are white dwarfs, and the explosion is triggered from the outside in. A thin shell of stolen helium detonates on the surface of one dwarf, driving a shock down into its heart that sets off the carbon below. The dwarf that exploded is, in this case, thought to be destroyed completely, leaving no bound core of its own. But its partner, the donor that had been feeding it, is suddenly cut loose from an orbit so tight and so fast that it is slung away at tremendous speed. A whole star kicked free of the wreckage without ever having been set on fire itself. Astronomers tag these double white dwarf runaways with a compact nickname drawn from that double detonation machinery, and they are leftovers of a thermonuclear explosion just as surely as our zombie stars are. But they are leftovers of a fundamentally different kind, and that difference is the entire reason for keeping the line sharp. The donor was never the fuel, so it does not carry the deep chemical wound that defines the true survivor. It is a witness to the blast, not a body that burned in it. This is exactly why, for the stars at the heart of our story, the sluggish spin and the heavy load of partial burning ash count for so much. Those are the marks that say this object was itself the bomb, not the one that merely stood beside it and was thrown clear. The two populations crisscross the same sky, both racing outward, both fleeing the scene of a thermonuclear explosion, and for any single fast star, it can take painstaking work to decide which story it belongs to. But conceptually, they fall on opposite sides of one clean divide. One is the partner that got away. The other is the bomb that somehow outlived its own blast. So suppose we have found one, a real partially burned remnant, racing through the galaxy with its scars laid bare. What becomes of it? What is the future of a star that survived its own destruction? The most likely answer is quietly poignant. The survivor's glowing now, swollen and overheated, because it absorbed an enormous shock of energy and is slowly bleeding that energy back out into space. But that energy will not last. There is no sustained nuclear furnace reignited in its core, no fresh fire keeping it bright. It is simply a hot, distended body cooling down. And as it cools, it will contract. The heat that lifted its degeneracy and puffed it up will leak away. The swelling will subside, and the star will slowly settle back toward the compact, dense state of an ordinary white dwarf. The best models suggest that these survivors, over time, will shrink and cool and eventually rejoin the long, slow procession of cooling white dwarfs, the faint embers that crowd our galaxy. The zombie star, in other words, is expected to eventually become a more or less normal-looking white dwarf again, albeit a chemically peculiar one, carrying its strange burned composition with it, as it fades into the dark over billions of years. It is a temporary apparition, a brief and dramatic phase in the wake of catastrophe, destined to cool into quiet anonymity. Could anything more dramatic happen instead? Could the survivor somehow be set off a second time, exploding again? Here we have to be especially careful to keep speculation from masquerading as prediction. In principle, for a white dwarf-like object to undergo a thermonuclear explosion, it needs to be pushed toward ignition, and that almost always requires a source of fresh mass, a companion to feed from or to merge with. But these survivors are, by their very nature, often violently ejected from their binaries, flung out alone into space, divorced from any partner that could feed them. A solitary remnant racing out of the galaxy has nothing to accrete, no way to gain the mass it would need to be lit again. And so for those, a second explosion seems unlikely. It is not impossible to imagine exotic circumstances, a survivor that retained a companion, or that someday encounters new material, but there is no good evidence that this commonly happens, and to assert that these stars are ticking bombs awaiting a second detonation would be to invent a story the data does not support. The honest answer is that for a lone survivor with nothing left to draw upon, a second blast is the unlikely outcome, not the expected one. Anything more is conjecture and should be labeled as such. We should also resist a tidier conclusion than the evidence allows in another direction. It is tempting, having assembled all this, to declare that every one of these weaker explosions leaves a survivor behind, that the incomplete blast always spares a core. But that is not established. The connection between this class of faint explosions and an actual surviving remnant is strong in some cases, and merely plausible in others. For the great majority of these supernovae seen in distant galaxies, we have never caught the survivor. We infer that one might be there from the faintness and slowness of the blast, but we have not seen it. Even in our best studied case, the surviving remnant interpretation was compelling but not perfectly clean. And the explosions themselves may vary, some perhaps leaving a substantial bound core, others perhaps disrupting more completely, others reaching the outcome by different paths entirely, as the merger origin of our own galaxy's confirmed remnant reminds us. So the careful statement is this: incomplete thermonuclear explosions can leave behind surviving bound remnants. We have found strong candidates for such survivors, and at least one confirmed example, and a growing class of runaway stars wears exactly the wounds the story predicts. That is a great deal. It is not the same as claiming that every such explosion always leaves a zombie star, and we should not pretend that it is. There is also a reason to care about all of this that reaches beyond the survivors themselves, and it loops us straight back to where we began. Remember that the bright, complete version of these explosions is one of the most important measuring tools in all of science, the cosmic ruler used to chart the distances to faraway galaxies and to measure how the universe is expanding. That entire method leans on the explosions being uniform, on each one shining with nearly the same true brightness, so that its apparent brightness can be read as a distance. But these weaker, incomplete explosions are fainter than the standard ones, and from far enough away, a faint explosion and a distant, ordinary one can be easy to confuse. If a subluminous event were mistaken for a normal one, it would look dimmer than it should, and therefore farther away than it really is, quietly corrupting the measurement. So part of the urgency in understanding these failed explosions is not just curiosity about the survivors they leave behind. It is about protecting the integrity of the ruler itself. Knowing how to spot the weaker events, how to recognize their telltale faintness and slowness and strange chemistry, is how astronomers keep the imposters from contaminating one of the most consequential measurements humanity has ever made. The survivors are not only a wonder in their own right, they are a clue to the difference between the explosions we can trust as rulers and the ones we cannot. There is one final confusion to lay to rest, because it is the easiest of all to fall into when you hear the words supernova and surviving remnant in the same breath. None of this has anything to do with a massive star collapsing into a black hole. That is a completely separate kind of stellar death, and it is worth stating the contrast plainly so the two never blur together. When a truly massive star, many times heavier than the sun, exhausts its fuel, its core can collapse inward under its own gravity, crushing matter into a neutron star or a black hole. And sometimes the outer star fails to explode outward at all, simply falling inward and disappearing. That is an implosion, a collapse, a story of gravity winning and matter being crushed into something denser and darker. What we have been describing is the precise opposite in spirit. There is no collapse here, no crushing inward, no black hole, no neutron star. There is an outward thermonuclear explosion that simply failed to carry through to completion, a fire that did its damage and ran out of strength, leaving a bound core spared by an explosion that ran short rather than crushed into being by an implosion that ran away. A zombie star is not something formed by collapse. It is something left over from a blast that didn't finish. Keeping that line sharp is essential, because the only thing the two phenomena truly share is the name supernova, and under that shared name hide two utterly different fates. So where does all of this leave us? Standing at the edge of what we know? It leaves us with one of the strangest objects in the cosmos, an object that forces us to revise a rule we thought was absolute. We began with a death so total and so reliable that we built a cosmic ruler out of it, an explosion that consumes a star utterly and leaves nothing behind. And we end having found that the rule has exceptions written into it, that under the right conditions the fire can stop short, the star can endure its own detonation, and a wounded, transformed, fleeing remnant can survive. We have a leading mechanism for how it happens, a slow flame that strangles itself by inflating the very star it is trying to destroy. We have a detailed portrait of the survivor, scarred in its chemistry, swollen in its body, racing across the sky. And most importantly, we have real objects that wear those scars. A growing family of chemically impossible runaway stars led by one faint fugitive fleeing the galaxy. A distant explosion caught before and after, with hints of a survivor in its ashes, and a 1,000-year-old wound in our own galaxy with a glowing remnant still beating at its heart. What we do not have is a finished story, and that is exactly as it should be. We are still arguing about which runaways are burned cores, and which are flung companions. We are still working out how many channels lead to a survivor and how often each one fires. We are still trying to catch an explosion and a survivor in the same act with enough clarity to remove all doubt. The subject is alive, in the way that frontiers always are, full of strong evidence and honest uncertainty held together in the same hand. But the central, astonishing fact stands. Somewhere out there, right now, there are stars that were lit on fire, partially consumed, chemically rewritten, and flung across the heavens by the force of their own explosions, and they are still here, still glowing, still holding themselves together under their own gravity as they cool toward a quiet future. Not alive, not resurrected, not healed, but enduring, carrying in every measurable property the record of a catastrophe that should have ended them and did not. There is something worth sitting with in that. We tend to think of destruction as final, of an explosion as the last word. And for most thermonuclear supernovae, it is, but nature, it turns out, keeps a few stars that slip through. That took the full force of an event designed to erase them, and came out the other side as something battered and strange and unmistakably marked. They are reminders that the universe is rarely as clean as our rules, that the most reliable processes can have ragged edges, and that even total annihilation occasionally leaves a witness. The next time you hear that a particular kind of dying star always destroys itself completely, you can hold in your mind these quiet exceptions, these fugitives fleeing the galaxy with the ashes of their own near-death written across their faces, and know that the cosmos is stranger and more forgiving of survival than even its own most dependable death allows. Thank you for staying with me through all of this, through the physics and the failures and the fugitive stars. If this kind of slow, careful journey through the universe is something you value, a quiet like or a subscribe, it genuinely helps more than you might think. And the next time you look up, remember that scattered through the dark are stars that died in fire and kept on going, and that the universe, for all its rules, still leaves room for the impossible to survive.